In addition to the overland oil pipelines connecting Russia with China, Russia has also developed a similar large-scale offshore project called Nord Stream, a pipeline laid along the bottom of the Baltic Sea to transport natural gas directly from Russia to European countries. Before Nord Stream 2 could become an offshore construction project, it existed first as a complex planning challenge that stretched on for many years. The objective was to create a direct connection between Russia's massive gas fields and Europe's major energy markets. However, the shortest line on a map was not necessarily the most feasible route on the seabed. Spanning roughly 130 kilometers, the proposed pipeline would pass through the territorial waters or exclusive economic zones of 5 different countries, each with its own environmental regulations, technical standards, and strategic interests tied to the Baltic Sea. From the earliest stages, the marine environment became a central factor shaping the entire planning process. The Baltic Sea is a semi-enclosed body of water with limited natural self-cleansing capacity and a long history of pollution from industrial activity, shipping, and coastal cities. Even minor disturbances to the seabed can resuspend contaminated sediments or disrupt sensitive ecosystems. For this reason, every country along the route required detailed environmental impact assessments before granting construction permits. To meet these requirements, survey teams carried out high-resolution mapping of the seafloor. Multi-beam sonar systems, seismic instruments, and unmanned underwater vehicles were used to analyze seabed topography, sediment layers, and potential risk zones. One unique challenge in the Baltic Sea is the presence of unexploded munitions left behind from World War I and World War II, scattered across the seafloor for decades. Whenever possible, the pipeline route was adjusted to avoid these hazards. In areas where avoidance was not feasible, the unexploded ordnance had to be neutralized through controlled detonations. To reduce the impact of underwater shock waves, contractors deployed bubble curtains around the blast sites, helping absorb acoustic energy and protect marine life. Only after the route was finalized, environmental risks were brought under control, and the legal requirements of each country were satisfied could Nord Stream 2 move into the construction phase. In many ways, this planning stage became the foundation that determined the success or failure of the entire project. After fabrication and concrete weight coating were completed, the steel pipe sections entered the transportation stage to coastal ports. This was a critical logistical phase, requiring precise coordination between manufacturing plants, storage yards, and port infrastructure. Each pipe section, weighing several tens of tons, was loaded onto specialized transport vehicles, or inland vessels, and moved to coastal transshipment ports in Finland and Germany. At the ports, the pipes were staged in large storage yards and arranged according to the planned installation sequence to optimize material flow. Heavy-duty cranes and handling systems were used to load, unload, and position the pipes safely, minimizing mechanical impact and the risk of damage. From these port facilities, the pipe sections were gradually transferred onto supply vessels or directly onto offshore pipe-laying ships, following carefully planned schedules that ensured a steady and uninterrupted supply of materials to ongoing offshore operations in the Baltic Sea. On the specialized pipe-laying vessels operating in the Baltic Sea, the entire deck is organized as a closed-loop industrial production line, where each installation step is carried out continuously in the middle of the ocean. The process begins when 2 pipe sections, each weighing up to approximately 24 tons, are positioned for welding and precisely aligned. Automated welding systems then complete the circumferential weld around the pipe, after which specialized inspection equipment immediately scans the entire weld to detect any structural defects or leaks. Only joints that meet all technical standards are allowed to proceed further along the line. Next, the welded joint is sealed with a dedicated protective system, combining heat shrink sleeves and elastic filler materials to prevent corrosion, while providing the flexibility needed for the pipeline to adapt to uneven seabed terrain. As the vessel slowly advances along the predefined route, the connected pipe sections are continuously guided into the water and gradually lowered into their designed position. Through tight coordination between transportation, installation, and positioning systems, this method enables the installation of up to 3 kilometers of pipeline per day, a pace rarely achieved in offshore construction. The pipeline installation process had to address geological and marine environmental challenges through seabed preparation and the management of crossings. While in many areas the seabed was smooth enough to keep the pipeline stable with minimal intervention, this condition did not apply along the entire route. In sections with uneven or rough seabed terrain, Specialized vessels were deployed ahead of pipe installation to level depressions using rock and gravel, creating a flat and stable foundation for the pipeline to rest on. By contrast, in shallow water areas where pipelines are exposed to strong wave action and hydrodynamic currents, the pipes could not be laid directly on the seabed. Instead, they were placed inside pre-excavated trenches, which were later backfilled to secure the pipeline in position. In addition to natural seabed conditions, the Nord Stream 2 route intersected with other existing subsea infrastructure. At locations where the pipeline crossed underwater power cables, telecommunications cables, or other pipelines, rock berms were installed to protect each utility at these crossing points. These protective measures ensured the structural integrity and long-term reliability of both systems sharing the seabed.